Hello, welcome to 7.3 Properties of Rational Exponents. So we're going to do a quick little review to warm up before we get into the lesson. So remember that you want to isolate the power, take the appropriate root of both sides, or in some cases it might not be that you take the root, you do the inverse operation of whatever the exponent is, like we're going to see in the first example, and then you continue with opposite operations if necessary. So in this first example, we haven't seen one quite like this yet. Normally we would do like the cubed root if it was x to the 1/3. And if we rewrite this as the cubed root of x, keep the -2 on the other side. Now we want to undo the cube root by taking the cube. That's the inverse operation. So then these will reduce down to just x, and -2 to the third power is -8. If we look over here at this one, it's a similar idea. We would divide both sides by 3. This reduces, becomes x to the fourth equals -1. And to undo a fourth power, we take the fourth root. But we have to remember that in this instance, because it's the fourth root of a negative number, and that's an even root, we can't do that. So we are going to say that this is no real solution. You would have complex solutions. Next one we're going to look at here is we have 2 times x plus 4 to the 1/3 power minus 3 equals -1. Again, our goal is to get the x part in parentheses by itself, so let's add 3 instead. This becomes 2 on this side, 2 times x plus 4 to the 1/3 power. Then we want to divide by 2. We do not want to distribute in this instance because we'd be breaking the order of operations. And 2 divided by 2 is 1. And then just like in number 1, we're going to do the opposite. We are going to take this to the third power. And now I can show you what happens if you don't change the root part. Remember that if it's power to a power, you multiply. 3 times 1/3 is 1. So then this problem becomes just x plus 4. Like our parenthesis around it would have a power of 1. But since that's just no longer necessary, and 1 to the third power is 1, now we can just subtract 4. And our answer would be x equals -3. So that's the one for this one here. Last one, x to the 1/2 minus 7 equals -3. We're going to add 7 to both sides. We want to get that x part by itself. We get 4. And then the opposite of taking something to the 1/2 power is to square it, because that's going to create our exponent of 1, which is what we want. 1/2 times 2 is 1. So then this side would be 16. Then our answer is x equals 16. Okay, so we're going to use some exponent rules to simplify here. One thing that you have to know, and if you want to mark this off to the side, in order to multiply between radicals, you have to have the same index. Note that we do not currently have the same index, because 4 is not equal to 3. What we're going to do instead is we're going to rewrite this. Since we do notice that they have the same radicand, that means we're going to have the same base when we write it as exponents. So this becomes 5 to the 3/4 power times 5 to the 1/3 power when I rewrite this. And then since we have the same base, we can add the exponents. In order to add 3/4 with 1/3 though, I need a common denominator. So I'm going to multiply this one by 4/4, and then I'm going to multiply this one by 3/3. So our new problem becomes 5 to the 9/12 plus 4/12, which if we add those together, we get 13/12. And there's our answer on this one. This next one is kind of nice though, because note, they do have the same index. If the index matches, then you can go ahead and just multiply the radicands, the terms inside. 25 times 5 is 75, so we have the cubed root of 75. Then, oh, actually that's wrong. That is not 75, it's 125. And then 125 breaks it down into 5 times 25, like we just saw. And I know we could have shortcutted that. We could have recognized that we would have got 5 cubed, but your answer ultimately just ends up being 5 for this problem. Here we have some more simplifying with exponent rules, so just some review from what we learned in the previous lesson. Here we would subtract the exponents. We would get 2 squared. 5 minus 3 is 2. And then we can multiply that or simplify it out to give us 4. This one, same idea. 2/3 and 1/3. We can subtract those. So this becomes 2 to the 1/3. Because 2/3 minus 1/3 is 1/3. Here, you saw this actually in your homework in the previous lesson. X to the square root of 3 to the power of square root of 3. This is power to a power, so you multiply. So this would be like the square root of 9, but a better way to write that is x to the 3rd. Here we're going to run into some more of those negative exponents. Remember that a negative exponent does not make the number or the base negative. It simply changes it into a fraction, and it takes what's in the numerator, brings it down to the denominator. So what we do is we just pull this down to the bottom, and then we change the exponent to a positive 2. And then we can simplify this. 5 squared is 25, so we're going to write it as 1 over 25. This one here, again, we have a negative exponent, so that's going to create a fraction. So 1 over 25 to the positive 1/2 power. And 1/2 as an exponent is the same as the square root of 25. And the square root of 25 is 1 over 5. We do want to be able to get down to this answer here. The simplified fraction version of 25 to the negative 1/2 is 1/5. That's the answer we're going to be expecting from you. And then this one, this is the same as taking the square root of a square root. So let's write that in fraction form, just as a refresher, what we do here. So this is 5 to the 1/2 to the 1/2 power. What we can assume then is we can take power to a power, so it's 5 to the 1/4 if I multiply. Or we could have just shortcutted that, and remember that you can multiply the index, and you end up getting the 4th root of 5. So on this next one, let's just use that shortcut. So our index on the inside is 2, the one on the outside is 3. If you multiply those, you're going to get the 6th root of 7. Now we're going to talk about rationalizing the denominator. This can be kind of a tedious process, and you've seen a little bit of it to an extent, but sometimes it's actually easier to simplify the problem before you try to rationalize the denominator. Like on this first one here, we instantly assume, oh, we got a radical on the bottom. We probably got to get rid of that. But since it's a square root over a square root, you can divide these. You can treat this like one big fraction and then simplify what's inside of it. So 45 divided by 5 is 9. So this is the same as the square root of 9, or just 3. Now this next one, unfortunately, we have the square root of 3 and the square root of 5 are not going to reduce the same way that we were able to reduce these two. So we need to be able to get rid of that square root of 5 on the denominator. And what we do to rationalize this is we multiply by the square root of 5 over the square root of 5. Really, we're just multiplying by 1, but this should get rid of the radical in the denominator. On the top, since these are both square roots, you can multiply them. So 3 times 5 is 15. The denominator, we would get 3 times the square root of 25, and the square root of 25 simplifies to just 5. Okay, so remember that this is just 5. So then we multiply 3 and 5 to give us 15. So here's our answer there. Okay, this time we have that radical in the denominator. We're still going to multiply by the square root of 5. But since we have 2 terms on top, we are actually going to distribute that to each term. So the top becomes the square root of 5 when you multiply by 1. If you want to put the 1 there, that's fine. And then 2 times 5 would be 10, but keep it under the square root. All over, hopefully we're catching on to this idea, but the square root of 5 and the square root of 5 ultimately just becomes a 5, no radical. Now we're going to step it up a little bit. These ones get even trickier. So this one is the square root of 7 over 5 plus 2 square roots of 3. Whenever you have a whole number plus a radical term, in this case 2 square root of 3, the way that we're going to rationalize the denominator is the same way we did it when we had complex numbers in the denominator. We had to multiply by the conjugate is what it's called, and it's just the same denominator. Like we're still going to see 5, 2, and the square root of 3. Oop, I did not write that well. square root of 3, 2 in front, and we just have to remember to put a negative sign in front of it. It's the opposite of whatever this sign is here. So then we're going to multiply by 5 minus 2 square root of 3. So we have to distribute here. So our numerator becomes 5 times the square root of 7. And then I'm going to take 7 times 3 in that next term. So that becomes 2 times the square root of 21. Over, that's our numerator, nothing's going to reduce there. The denominator, we are going to FOIL, because this is like having two sets of parentheses. So 5 times 5 would be 25. 5 times negative 2 square roots of 3 is negative 10 square root of 3. 2 square root of 3 times positive 5 is positive 10 square root of 3. And then 2 times negative 2 square root of 3. This is where I want you guys to pause and think for a second. So if I am multiplying 2 square root of 3 times another 2 square root of 3, what you're going to do is multiply the whole numbers first, so 2 and 2, which makes 4. Then you're going to multiply the square root of 3 and the square root of 3. That ultimately becomes the square root of 9, or just regular 3. So then this is going to become 12. And since it's a minus here, I need to write negative 12. Now, if I did this correctly, we should end with no radicals in the denominator. We'll still have some in the numerator, but... So I'm going to keep the top the same, because nothing reduces there. In the denominator, we have a negative 10 square root of 3 and a positive 10 square root of 3. Those are going to simplify down to 0. So we're left with 25 minus 12, and we can reduce that. 25 minus 12 is 13. So our numerator and our final answer here is 5 square root of 7 minus 2 square root of 21 all over 13. Okay, now this one probably doesn't look as bad as that last one, but it still can be kind of tricky. So we have a cubed root and a cubed root here. We have a 2 as the whole number, and we can reduce this because we know that we can divide 3 by 9. So if I were to simplify this, I can keep the 2 on top, and break this down to a 1, and then I'm going to break this down to a 3. This is like taking 3/9 and simplifying it to 1/3. Now I still have the cubed root of 3 here. So what I'm going to do to rationalize the denominator is I need to multiply by a cubed root. But before I fill in that number, I want to think about this for a second. When you're doing it with a square root, you multiply by the same number. But if I multiply by a cubed root of 3, watch what happens. I would get 2 times the cubed root of 3 over the cubed root of 9. Now the cubed root of 9 doesn't work out for us. It doesn't get rid of the radical because 9 is not a perfect cube. So we're going to backtrack here. We need to think about what number associated with 3 is going to give us a perfect cube so that it breaks down and we get a 3 on the bottom, but because it's a perfect cube. And that number is 27. So our goal is to get a cubed root of 27, because we can multiply with a 3 to get to 27, and the number that we're missing is actually 9, because that's the same as 3 squared. We're trying to get 3 groups of the same number under the cubed root. So then what ends up happening is 3 times 9 gives us 27, and the cubed root of 27 gives us 3 in the denominator. The numerator, I also had to multiply by, the cubed root of 9, so that is still next to this 2 here. We're going to practice these ones a couple times, and it might be a little hard to grasp in the video, but just give it a shot. You will definitely get an opportunity to see one of these problems again. Last part here is the adding and subtracting of radicals. In order to add and subtract, it is even more specific. You have to have both the matching index and your radicand has to be identical. So notice we have a 5 and a 625. We can't add those until they're identical. Hopefully this will break down in a way that we can, and then I'll show you what to do after you have the same index and radicand. So I'm going to break down 625. That's the same as 25 times 25. This breaks into 5 and 5, 5 and 5. So I have a group of 5s that I can pull out. They are going to multiply with this 4 here. So now the new problem is 6 times the cubed root of 5 plus 20, because it's 5 times 4, and I do have a cubed root of 5 inside. This problem here, when you're adding radicals, now that I have the matching index and the matching radicand, the 5s, it's like if you were adding 6x with 20x. That becomes 26x. The x part doesn't change, it's just the coefficients. So here this would become 26 times the cubed root of 5. And that is our answer there. So hopefully these problems will break down in a way that we can see what we can add. So if you notice here, probably should have started with this one, but 2 and 7 are the only thing that's going to change because it's the 6th root of 3 and the 6th root of 3 on both terms. So this is our answer. 2 plus 7 gave us the 9. Same thing for subtraction. If you have the matching index, matching radicand, you can just subtract the numbers out front. So 8 minus 3 would be 5. So 5 square root of x is our answer on this one. If you have matching exponents, like h to the 1/4, h to the 1/4, and your bases are the same, you can also do the same thing. Because if I were to write this in the radical format, I would have matching indices, like what we saw up here. So I'm just going to save you some time. This would be negative 3 gh to the 1/4 power. Because I took 3 minus 6 to get us that negative. This even works if you have the same term behind the 5 and the 3 in this instance, because this would be the same as having 5 times the 4th root of 4 to the 3rd power minus 3 times the 4th root of 4 to the 3rd power. We would have matching indices and a matching radicand in both, so that's why we don't even need to rewrite it. It's not a necessary step. Just subtract your coefficients. So it would be 2 times 4 to the 3/4 power. This one here, we don't have matching radicands, so I'm going to break this down, see if I can get anything similar. This becomes 3. It's probably second nature to you to want to break this down now. Hopefully it is anyway. So this would be 3 times the cubed root of 3 minus the cubed root of 3. Now, if you don't see a number in front, you can just assume that 1 is the coefficient. So this is like taking 3 minus 1, which would be 2 times the cubed root of 3. And there's our answer on that one. All right, last set here. Perform the indicated operation. So again, we want to break down if possible. So if we look at this first one, it's the 4th root of 6x to the 5th, and then it's plus x, 4th root of 6x. So the only thing that I see we're going to be able to break down is x to the 5th. We can take out one group of 4 from that. So if I break that down, I'm going to take out an x, and then inside I'm still going to have a 6 and an x. So plus x times the 4th root of 6x. Perfect. Then I'm going to just add my two pieces behind here. Sorry, the two pieces in front, the coefficients, which are 2x and x. And if you were to add 2x and x normally, that would give you 3x, and then the 4th root of 6x stays the same. The last example, you did see this in your homework as well. You cannot add 2 and the square root of 3, unfortunately. Like if this was x squared times x to the 3rd, we'd get x to the 5th because we'd add them. So you just leave it as an expression format, so it's 2 plus the square root of 3, because you can't add a whole number with a radical. And that's how you just leave the answer, even though it looks kind of weird.